Okay, the unit we're going to work on is proportions, and basically proportions are very related to the binomial. In fact, we are going to ultimately develop the normal approximation for the binomial. So we need to review back on binomials. So real quickly, first off, binomials are a type of Bernoulli trial. So are geometrics, but a Bernoulli trial is a random experiment with exactly two possible outcomes, success and failure, in which the probability of success is the same every time the experiment is conducted. Now, one thing to be careful about is you may have multiple options. You may have option A, B, C, D, and E, but the probability of guessing A would be 20% regardless. So basically, the probability would be success, the probability of guessing correctly, and the rest of it would be the probability of failure. So just because you have multiple options doesn't mean it can't be broken down to success, failure. It just needs to know yes, no. And you may have multiple failures, but only one success, only one type of probability for success. We generally define success as P and failure as Q, where Q equals 1 minus P. And if we ever use Q, we need to make sure we make a little note off to the side that it's 1 minus P. The probability of success must be constant. Trials must be independent. This is true for all binomials. However, we do have a little bit of an exception to that. When we don't have an infinite population, the trials are not independent, but it's still okay to proceed as long as the sample is smaller than 10% of the population. And we've been saying that for the normal for quite some time. So the binomial gives us the probability for a random variable that counts the number of successes in a fixed number of Bernoulli trials. And what sets a binomial apart from the geometric is the geometric continues until the first success. So in other words, we may try and try and try and try and never ever achieve that first success. However, a binomial just says we're going to continue for 10 times. We're going to do this 5 times, or we're going to do it 100 times. But we have a fixed number of attempts that we're going to agree on before we start. Again, the characteristics has 2 outcomes. The trials are independent. The probability of success is constant. And the number of trials is what I would say that you need to focus on. The number of trials is independent. This right here represents the formula, and you can read that right here. N is the number of trials, K is the number of successes, probability of success raised to the number of successes, and then Q is the probability of failure, and then this would be N minus X, so this would be the number of failures, all right? The equations for mean, variance, and standard deviation will be given to you if you need them, regardless whether it's on the AP exam or other, so not something you need to memorize. However, by now you should be able to know the expected value is NP, and truthfully, we use this so much you might want to have that memorized as well. So binomials are usually phrased as what is the probability of some number of successes in a given number of trials? So in other words, what's the probability of 3 successes in 10 trials? If we have a specific number of successes, exactly one agreed upon value for successes, probability is 0 successes. What's the probability of 5 successes? But we have a singular value. This is going to make it a binomial PDF when we actually go to put it into the calculator. What is the probability of no more than some number of successes in a given number of trials? Again, given number of trials lets me know that this is binomial. No more than some number of successes means that I can have multiple successes. So if I had 5 trials, I could have 0 success, 1 success, 2, 3, 4, or 5, and no more might mean no more than 2. Well, obviously I circled 3 potential values: the probability of 0, the probability of 1, and the probability of 2. So this essentially is going to be a CDF problem, which is a combination of the individual PDFs. So that's the probability of 0 plus the probability of 1 success plus the probability of 2 successes. Finally, We also have what's the probability of at least some number of successes in a given number of trials. All right. And this also is going to be a CDF. Anytime you have a list of trials, or you have a situation where they ask for more, what's the probability of having more than this? Probability of having at least this. When we do that, 0 is not included because we want the probability of at least 3. That means we want 3, 4, and more. Probability of more than 2. That means we want 3, 4, and more. Or the probability of at least 1. That means we want the probability 1 or more. Anytime 0 is not one of our possible, not included in our possible number of successes, we're going to be doing 1 minus the binomial CDF. So here's a couple quick reminders. Suppose the probability of having a defective light bulb is 0.15. Given a box of 30 light bulbs, what's the probability that 2 are defective? So what we have here is we want 30, choose 2, and we have 0.15, the probability of defective to the second power. 30 minus 2 is 28. And this is going to be a second var's binomial PDF. Trials are 30, P is 0.5, X value is 2. Or if we were writing it out, we go binom PDF, trials are 30, the probability of a success is 0.15, and we want exactly 2. As if I were making my list of possible outcomes, this is what it looked like, 0, 1, 2, 3, all the way to 30, but I'm only circling one value. The fact that I'm circling one value makes this a PDF. Running this real quickly, second vars, binomial PDF, trials is 30, probability is 0.15, and my X value is 2. And we end up getting 0.1003. The next one, given a box of 30 light bulbs, what's the probability that no more than 2 are defective? So if I make my list of possible outcomes, I have 0, 1, 2, 3, 4, ... all the way to 30, but no more than 2 means I want 0, 1, or 2, because that's no more than 2, that's no more than 2, that's no more than 2. Well, I circled more than one value, so this makes this a CDF, whereas right here I circled one value, which makes this a PDF. So in this case, I like to do the bookend, so I do the lowest value and the highest value and put a plus ... in the middle. So we want the probability, so we have 30 choose 0, because that's the lowest, 0.15 to the 0, 0.85 to the 30th, plus ... plus 30 choose 2, 0.15 to the second, 0.85 to the 28th, because remember, 1 minus 0.15 is 0.85. And what we're really doing is we're doing the PDF of 0 plus the PDF of 1 plus the PDF of 2 to get this answer. And in calculator speak, this is going to be a binom CDF. 30 is my number of trials, 0.15 is the probability. And if you notice, these are almost exactly the same. The difference is that's a PDF, which means specifically this value. This is a CDF, which means it includes the top value and any other values that are below it, which would be 0 and 1 in this case. So second vars, binomial, CDF, trials is 30, probability is 0.15, and my X value is 2. And I end up getting 0.1514, which is what we have here. Now, this actually makes sense logically because this is a little bit larger than that. This is 0.10, this is 0.15. And the reason is this only had one possible outcome, where this one had 3, 0, 1, or 2. So this is just 2, this is 0 or 1 or 2, and the sum of those probabilities becomes 0.15, 0.4. So we'd expect it to be a little bit larger. Now, the next one is tricky. Given a box of 30 light bulbs, what's the probability that at least 28 are not defective? So first off, the probability of not defective is 0.85. So we switched this around. We're no longer working with defectives, we're working with not defectives. Also, I want to point out, let's go ahead and make a list of possible outcomes. So we have 0, 1, 2, ... 27, 28, 29, all the way to 30. This is my list of possible outcomes. Well, if I notice 0 is not included in this, all right? And that's going to be, excuse me, it should have been at least 28. I should have just circled all the way to 28, not the 27. This is what should have been circled. And I don't want the 27. I want 28, 29, and 30. These are the values I want right here. And everything below that line, I do not want. So the best way to go ahead showing my work is still doing the bookend scenario. So the lowest value I want, 30, choose 28. We changed our probability to 0.85 because we're working with not defectives. So 0.85 to the 28. 30 minus that gives me 2. Now, 30 choose 30 is 0.85 to the 30th, 0.15 to the 0. And when I go to the calculator, what I'm actually going to do is 1 minus, and it's a binomial CDF because we have multiple values and 0 is not included. 0 not being included tells me it's going to be a 1 minus. So 1 minus binomial CDF, trials is 30. The probability of success is 0.85. And the highest value I don't want is 27. Because when I subtract, I want what's left over. So here we go. 1 minus second vars binomial CDF. Trials is 30. My probability is 0.85. And the highest value I didn't want was 27. And again, I get 0.1514. Now, someone asked a really good question. They asked, hey, these give me the same answers. Would I need, if I did this first one, would I need to show work on the second one? And for this type of problem, you absolutely would, because they really are different problems. They just happen to be set up to give you the same answer. Now, if you wanted to say 1 minus that, they might accept it, but you're better off showing all your work. Okay, so moving on, continuing our study of the binomial. Want to give you some idea as to a binomial shape because it varies depending on the probability. So in this case, we have trials in each one of these 3 graphs. We have trials of 10, so 10 possible outcomes, 10 possible successes. All right, so our sample size 10. This one has a probability of 0.2. So let's put this into a scenario that actually makes sense. Well, first off, our expected value formula for the binomial is just NP. All right, because that's what we're going to need, that information when we go about doing this. Now, let's just assume that someone's playing basketball, they're not too good, they only make 20% of their shots. So if they were to shoot 10 times, 10 times 0.2 is 2. And so you would expect them on average, if they shot 10 times, to make 2 of them. Now, they might make less or they might make more. However, the most they can make is 10 and the fewest they can make is 0. So we'd expect it to be centered on 2 and then distributed each way. Well, consequently, what we end up with, since we can't go lower than 0, we end up being skewed to the right. So this one is skewed right. And we're going to make a general concept about this in a moment. Here, we're going to skip the middle one for the moment, and we're going to say, all right, this guy's a little bit better at basketball. It's pretty good, makes about 80% of their shots. If they only shoot 10 times, you would expect them to make 10 times 0.8 or 8 shots. So you'd expect this to be centered around 8. Now, they might have a really bad night and make as few as 0, but if they're only shooting 10 times, the most they could ever make is 10. So we're centered at 8, and we could stretch this all the way out to 0, but that's really unlikely. We're more likely to make 10 than we are to make 0. So we end up getting this shape right here, which is skewed left because it's been stretched to the left. On the other hand, someone else just makes 50% of the shots, and regardless how many times you shoot it, it's going to be centered on that mean. It's going to be nice and mound shape. So the expected value, that's not a very good mound, but it's nice and mound shape. 10 times 0.5 is 5, so we'd expect it to be centered on 5. And you might do really bad, or you might do really well, and they're about equal, and they should be equally plausible because they're equal distance apart with a probability of 0.5. So this one ends up giving us a mound shape. Now, what that means is this. If our probability is less than 0.5, it's skewed to the right. So less than 0.5, it's going to be skewed to the right. And the further it is, as you get closer to 0, the more skewness it's going to have. Over here, as our probability gets greater than 0.5, as we get greater than 0.5, we're going to move up, and so we're going to be skewed to the left. All right, this will be skewed to the left, and the closer I get to one hole, the further skewed to the left it is. In other words, the closer up, closer to the right I'm going to be. And if my probability equals 0.5, we're going to be mound shaped. So probability less than 0.5, skewed right, greater than 5, skewed left, and equal to 0.5 is mound shape. Well, that's interesting, and that applies to the binomial. But as you know, I've said before that as n increases, as our sample size increases, things become normal. So how would that apply if we increased, instead of having a 10, we had a larger sample size? So we're going to continue with an 80% probability, but we're going to increase our sample size to 20 and then to 50 and see what would happen. Well, once again, our expected value formula, since we're working with a binomial, is still NP. In this case, 20 times 0.8 is 16. And sure enough, we're centered at 16. And one thing I've noticed is, yes, I can make as few as 0, but this is starting to get a lot taller because we expect the more times we do it to get closer to the expected value. As the more times we do it, we decrease our sampling error and we center about the mean a bit more. So this one, while you can definitely see it's somewhat skewed, it's still skewed to the left. Still skewed to the left because our probability is greater than 0.5, but it's less skewed. When I look at this one, it's like, wow, this is starting to look really normal. I mean, obviously we can see a little bit of skewness, but it's looking pretty normal. This is looking almost mound shape. And my expected value is 8 times 0.8 times 50 gives me 40. So we're centered at 40. Now, I'm looking at this and going, you know what? We're getting closer and closer to the normal. So when is our sample size large enough to say, you know what? It's approximately normal. So we have a rule, and that rule is that it's actually 2 rules, and you have to satisfy both of them. In other words, our sample size must be large enough to use the normal approximation, and NP must be greater than or equal to 10, and NQ, the number of failures, must be greater than or equal to 10. So we're going to head and use this value right here and test this one out and see what happens. So if I do that, I'm going to go, well, 50 times 0.8 is 40. That's greater than or equal to 10. That condition is satisfied. But I've only satisfied one of the requirements, so I need to go back and check the other one. So the next one, my sample size 50, but my failure is 1 minus 0.8, which happens to be 0.2. In this case, that's 10. And last I knew, 10 was also greater than 10, greater than or equal to 10. So these two conditions have both been satisfied. Now we can look and say that this one's barely satisfied. And you can see, well, there's a little bit more skewness. So you can see as we get greater than 10, we're going to become even more normal. So as we become greater than or equal to 10, it becomes closer to the normal. But at any rate, if we satisfy these conditions, our sample is large enough to use the normal approximation for the binomial. So here's a scenario. Let's check it out. An archer with an 80% bullseye rate will be shooting 2,000 arrows. What are the mean? Well, the mean is 2,000 times 0.8 is 1,600. Our standard deviation is 2,000 times 0.8 times 0.2. Take the radical and we get 17.89. Is a normal model appropriate here? Well, in this case, 2,000 times 0.8 is 1,600. That's definitely greater than 10. And 2,000 times 0.2 is 400. So that's also greater than 10. Both NP and NQ are greater than 10. The sample is large enough to use the normal approximation. Okay, so that'll end this video, and then we'll move on to talk about proportions and confidence intervals.